Okay, good morning everyone. Take your seats please. Thank you. So this morning we're going to talk about the second of the triumvirate of new mathematical expressions which we encounter in this course. So we have the gradient, the divergence and the curl. Today we're going to go through the divergence. The divergence in a nutshell is a property of a vector field, and it's the tendency of that vector field to diverge, that is to spread out as a function of position within that field. So let's just recall our friend the Nabla operator, which is the operator which we use for all of our new expressions in this course. So Nabla is a vector operator of that form. The divergence of some vector field is often written just as div f. It's also written as the dot product of the Nabla operator with your vector field. And if we assume that when we're talking about some vector field f, what we're talking about is three components, fx in the I direction, fy in the j direction, and fz in the k direction, then the divergence of that vector field is simply dfx by dx plus dfy by dy plus dfz by dz. So this is the definition of the divergence. And as we'll discuss in a moment, and as I've already said, and as is also obvious from the name, which is appropriate, this is the tendency of a vector field to spread out or to compress at some point. And again, the easiest way, just as when we were talking about surface integrals of vector fields representing the flux of a vector field through a surface, the easiest way to conceptualize this is to imagine that your vector field is somehow a flow, and so the divergence of your vector field tells you about the tendency of that flow to spread out or to compress as a function of position in the vector field. Okay, so this is what I've just said then. So a reminder that we know Nabla is our vector operator. The divergence is written both as div f and as the dot product of Nabla with our vector field, and has this form. So the divergence, you'll recall that the gradient takes a scalar field and returns a vector field. The divergence does the opposite. Bless you. The divergence takes a vector field and returns a scalar field. So in the case of the gradient, you have your scalar field, which is a whole lot of numbers distributed through space, and the gradient tells you the direction and rate of greatest change. The divergence is a scalar property of your vector field, so it has a scalar value at every single position in your vector field, which tells you about, as I said, how much the field is diverging or compressing. Now, a vector field for which the divergence equals 0 is called solenoidal, or sometimes slightly more obviously incompressible. And we will see later on in this lecture how one of the best known vector fields in physics is, in fact, several of the best-known vector fields in physics are, in fact, solenoidal or incompressible. Okay, so here's a two-dimensional sketch of a vector field, and as I said, the divergence measures how much the vector field is flowing out of some given point in your vector field, which would be a positive divergence. Okay, so if you draw a small area, we'll come to the definition of the divergence in a moment. But if I pick some point and I draw a small area around that point, and I sum up how much of the field is flowing in and out at that point, then a positive divergence means more is flowing out, and a negative divergence means more is flowing in. Okay, so positive divergence, as the name suggests, is diverging, and negative divergence is a field which is compressing. So we'll see this later in the lecture in more detail, but just again, let me repeat the warnings that I made previously in the lecture, in the lecture series, which is that you cannot just look at a sketch of a vector field or conceptualize or visualize it in your head and go, yes, clearly that's outwards flowing, clearly that's an expanding vector field, clearly the divergence is positive, or perhaps in some cases you visualize it the other way around and say the divergence is negative. You cannot trust your instincts on these things. You cannot sketch something and trust your instinct to get it right, and we'll see, as I say, we'll see some example of that later on in the lecture. Okay, so let's just do some incredibly trivial examples, just to be sure that we know what we're doing. So if we have some vector field, which in this case is x squared y I plus x y z j minus x squared y squared k. So in this case, I identify this as fx, this is fy, and this is fz, and that's always implicit, you know, when I have a vector field f that I'm going to call these three components fx, fy, and fz. Then the divergence of f in this case is going to be the derivative of this with respect to x, so that's going to be 2xy. It's going to be plus the derivative of this with respect to y, which is going to be xz, and it's going to be plus the derivative of this with respect to z. Well, in fact, that's 0, so that term there is 0, so we don't have a term from that at all. So the divergence of this vector field is 2xy plus xz. That's a scalar quantity that tells you how much the field is diverging at that point. And we'll return to the position vector in a moment, but let's just visualize that field and its divergence. So this is that vector field which we just were looking at, the field f here. This is its divergence, 2xy plus xz, which hopefully agrees with that. It does, good. So this is a vector field sketch of that vector field. And what you can see is that using the scale which I've chosen, the vectors, unsurprisingly, are not very large near the origin, and they grow to be large in the four corners here. If I look at the divergence now, so the right-hand figure here is a 3D plot of this scalar value, the divergence, as a function of this vector field, then we can see that there are blue regions where the field has a negative divergence. That means the field, the vectors, if you looked at them closely in these regions, are compressing in this region, and those regions are sort of bounded by regions with positive divergence, where actually if you looked at the vector field, it would be expanding. So I should say I've already given you the warning that if you sketch out a vector field and it looks like it's expanding, you might be fooling yourself. It doesn't necessarily have positive divergence, that's true. But if a field does have positive divergence, then it certainly will look like it is expanding. So, you know, zooming in on these regions, the blue and the brown regions here where you have negative and then positive divergence, if you made this plot yourself, which incidentally is very, very straightforward to make in Mathematica or from Alpha, and you can zoom in and you can actually get quite an intuitive feel of what's happening to the divergence in these regions. What about the divergence of the position vector? So the position vector r is just xi plus yj plus zk. So the divergence of the position vector is just, well, that's 1. The d by dx of x is 1. d by dy of y is 1. And d by dz of z is 1. So that just equals 3. And in fact, this is immediately obvious, I think, the divergence of the position vector has a value which is equal to the number of dimensions you have. We'll return later on in the lecture to explaining why one of our best known vector fields in fact doesn't have a positive divergence, is in fact solenoidal. But let me just note here, if you're wondering what's going on here, if you imagine some small volume, then the surface area of that volume in the radial direction increases with r squared. And the length of this vector also increases with r, and the r squared plus the r actually gives you the r3, r cubed term. You'll see a little bit more later on in the lecture what I mean by that. Okay, so let's derive the expression for the divergence. So the divergence is the surface integral of the vector field around a point in the limit that that volume shrinks to 0. So what I mean here is I have my three-dimensional space, x, y, z. I have some vector field in here. I'm not going to draw all of the arrows, but you imagine that this is a vector field permeated by your arrows, which represent the strength and direction of your vector field. And I take some volume in this vector field, and I evaluate the surface integral of that volume. Okay. And you'll realise from the work that we were doing in previous weeks on the surface integral of a vector field then, and as I've just mentioned, that's the total amount of flux flowing in and out of that volume. Okay? And then if we take this volume and we shrink it down in the limit where this volume becomes 0, then that tells you how much flux of that vector field is flowing in or out of the vector field at that point. So, the divergence of our vector field, which could also be written with a lowercase d, is the dot product of nabla with our vector field, is the limit as the volume goes to 0 of the surface integral associated with my volume V, of the surface integral of my vector field around that volume per unit volume. Okay? So that should be the same expression which is up there. It is, that's good. And of course, recall this is this expression here, n hat scalar ds is entirely equivalent to the vector area ds, and the two are used interchangeably. Okay, so how do we go from this definition of the divergence, which I think makes sense, okay? You want to know how much of your vector field is flowing in and out, and then you want to go down to the limit where it's just at a point. So as a physical definition, it makes sense. How do we go from this to the mathematical definition which we have? So, we do the following. We draw a cube as our first step. So, this is one of the shapes that I usually can manage to draw reasonably well, unlike my axes in this case. X, Y, no. Right, what I'm going to do is I'm going to rotate my coordinate system here, just because we're all used to thinking about x first when we talk about axes, and it's slightly easier in this case to have x going this way. So I normally have x, y, z. So in order to keep the handedness of my coordinate system the same, but have x over here, then I just rotate my coordinate system around like this. So this becomes z, this becomes x, and this becomes y. now disagrees with that. Okay, so I have some Q, which is some volume in my coordinate system. And the centre of this cube is at coordinates x, y, z. The length of the sides of this cube are delta x, delta z, and delta y, which means that the volume of the cube equals delta x times delta y times delta z. And what I'm going to do is I'm going to call this face here the plus x face. So this is the face pointing in the direction of the x-axis at the positive increment from the centre side, and I'm going to call this face here the minus x side. So this is the plus x side. So what I'm going to do first of all is I'm going to evaluate the sum of the surface integrals of this vector field through the plus x and minus x faces. Now, of course, in the x direction, the unit vector is simply I. And I'm going to assume again that my vector field f has the form fx in the I direction plus fy in the j direction plus fz in the k direction. All right, so what I'm going to do when I consider my surface integral, I'm going to consider my surface integral as acting at the centre of that face. Okay, so what are the coordinates of the centre of the plus x face? So the coordinates of the centre of the plus x face are x plus delta x over 2, so they're x plus half the length of this side, because the centre of the cube is at x, y, z, and then they're at y and they're at z. So we're considering the plus x face now. The coordinates are x plus delta x over 2, y, and z. Okay, so our surface integral then for the plus x face, f n ds, is equal to the x component of my vector field, because of course my vector field here, the x component is operating in the I direction. We're dot producting that with the unit vector in the x direction, which is I. So this is just the value of the x component of the vector field at the coordinates x plus delta x over 2, y, and z, multiplied by the area of the plus x face. And if you look at this diagram, you'll see the area of the plus x face is delta z times delta y. Delta y, delta z. And if I do the same thing for the negative x face, then I get fx at the coordinates x minus delta x over 2. Sorry, this is minus. It's pointing in the other direction. It's now pointing in the minus I direction. X to the minus delta x over 2 y z, again, by the same area, delta y times delta z. So then the total surface integral for the x faces is given by f of x at the coordinate x plus delta x over 2, y, z, minus fx at the coordinates x minus delta x over 2 y z, all times by delta y delta z. And of course, when we take the limit where this volume goes to 0, what we're doing along each of our axes is we're taking the limit where the length, the small increment along the axis goes to 0. So we're taking here the limit where delta x goes to 0. So we can already see that this is probably going to reduce to a familiar form as our definition of a partial derivative, but we want it to be divided by delta x, which will give us the right form. So if I divide this by a delta x, that means I have to put, imagine that I've left enough space, that's also multiplied by a delta x. And now in the limit where delta x goes to 0, this becomes the partial derivative of fx with respect to x times delta x, delta y, delta z. So we can do the same thing for the plus and minus y sides and the plus and minus z sides, and then we find that our surface, our total surface integral for all 6 sides equals dfx by dx plus dfy by dy plus dfz by dz, all times by the volume of the cube, delta x, delta y, delta z. And you'll recall that our definition of the divergence was the surface integral per unit volume. So we're dividing this out now, and therefore we end up with our expression that the divergence, starting with our original definition, equals dfx by dx, dfy by dy, dfz, dz. So this is how you end up with the formal definition of the divergence, which you use when you're calculating problems, from the relatively straightforward to conceptualize physics thing, which is you're taking the surface integral around some point. Wake up. All right. So I want to quickly touch now on what is the... So I want to quickly touch now on what is the form of the divergence in other curvy coordinate systems. In particular, the two other coordinate systems which we use in this course and which you mainly use in physics are cylindrical and spherical polars. And you'll recall we've talked previously about what the scale factors are. Okay? And you can calculate them, you can calculate these expressions explicitly, but you can also visualize geometrically your coordinate system and work out what these scale factors are, and they're relatively straightforward. So this is our expression. H1, H2, H3 are the scale factors associated with your curvy linear coordinate system. So the first of these non-Cartesian curvy linear coordinate systems we looked at was cylindrical polars. And in the case of cylindrical polars, the scale factors, if you'll recall, are 1, r, and 1. Okay? So the only deviation from Cartesian is the fact that you have the plane polar Jacobian component of r. So when you sweep through some angle, the distance traversed is r d theta. And when you put in the scale factors 1, r1 into the expression which was on the previous slide, which is in the notes but is not in the syllabus, so you don't have to memorize it, then you end up with this expression here for the divergence in cylindrical polar coordinates. You do not need to memorize this. It's just to show you the form of it. If you do the same thing for spherical polar coordinates, where the scale factors are 1 r and r sine theta, if you recall, then you end up with a slightly more complicated expression, which is this one here. Again, you don't need to memorize it. But we are going to use this expression in the following exercise, where we work out the divergence of the electric field. So quite often in physics, when you're thinking about the electric field, the gravitational field, for example, you're talking about fields which are radially symmetric, i.e. they come out radially and isotropically from some point. In that case, the d theta and d phi terms in this expression don't matter at all, and all that's important is the radial term. So in spherical polars, for a radial field, the divergence of that field is given by 1 over r squared d by dr of r squared times the radial component of that vector d. So this is an important expression. It's useful for you to know this. It's not that much more for you to add to your memory locker, but again, this will probably be given if it's required in an exam. Okay, so let's go on then to this important example for the divergence of a field, which I've alluded to at the start of the lecture, which is what is the divergence of the electric field? What is the divergence of the electric field? Now, we all know that the electric field is a field which works radially, and although it falls off with distance, that's not a very good example, illustration of 1 over r squared, we can clearly see that the electric field, clearly it's flowing downwards, right? So intuitively, when you look at the electric field, you know this must be a diverging field. So in common human life, when you have an expression like this with a question mark at the end, you really don't know the answer. In science, it's nearly always the case that if you have a question like this with a question mark on the end, then the answer is no. Okay. So it's true. So, the electric field, as you know, has the form Q r hat over 4 pi epsilon naught r squared. So we'll just simplify that. We'll just call that C, where C bundles all our Q over 4 pi epsilon naught in. C r hat over r squared. So what then is the divergence of the electric field? So the divergence of the electric field, the C is a constant, so I'm just going to take that out to the front. There's a 1 over r squared, so this becomes C over r squared, and then I want d by dr of fr. So my fr in this case is 1 over r squared, but I'm multiplying that by r squared. So I want d by dr of r squared over r squared, which is 1, and the number 1 doesn't change as a function of distance, so therefore this equals 0, therefore the divergence of the electric field is 0. So again, this is just you knew that we were going to get to this point, but if you sketch the electric field, you visualize the electric field, it looks like it's diverging, but the electric field, in fact, isn't diverging at all. So how can you understand this? So you can understand this in the following way. If I have spherical polar coordinate system, and I have my point here with my polar angle theta, and if I move it some amount here, d theta, this projects down onto my xy plane, and I have my angle phi that it makes with the xy coordinate, and I move that some d phi. then I end up with a shape that looks a bit like that, except. If I zoom in on that shape, then I have a shape that looks something like this. Okay, so I have some little volume here in space. My electric field is a field which is acting radially out like that. And then the point is, if I take this volume, what I want to know is my electric field is only flowing in and out of these two surfaces. All the other surfaces of this shape are perpendicular to the electric field. So there's no electric field flowing through them. So I want to consider this surface here and this surface here. Well, the area of these surfaces is proportional to r squared, and you can see that by considering the surface element in spherical polar coordinates, which is r squared sine theta, but it's also just obvious geometrically. But the magnitude of the electric field is proportional to r to the minus 2. Okay. So you have, if you go out some small distance, some small increment r, then your surface through which your electric field is flowing has increased by r squared, but the strength of the field has decreased by 1 over r squared, which is why you have exactly as much electric field flowing in here as you have flowing out there, and the net amount of field flowing in and out of this volume is 0. Okay? So that is the reason why the divergence of the electric field is 0. Okay, we've done that. And we've done that too. Okay. So let me now introduce you to the, there are a couple of second order vector calculus terms which you need to know or to understand, but by far the most important of them is this one here, which is called the Laplacian. So we know that if F is a conservative field, then F is the gradient of some scalar potential. So F here is a conservative field, and U is a scalar potential. So the divergence of F is then d2u by dx squared plus d2u by dy squared plus d2u by dz squared. And this is also known as del squared u, which is, as it says on the screen, the Laplacian. So there's a number of things that you can do with the Laplacian. As I already mentioned earlier on in the lecture, if you have a vector field for which the divergence is 0, such as the electric field, which we've just looked at, that's a particularly interesting type of field. They're called incompressible or solenoidal. So, for example, you could take the electric potential or the gravitational potential, which is, of course, directly analogous to the electric field, given its form. You could take those, calculate directly the Laplacian, and if the Laplacian of your scalar field is 0, then you know that the vector field, the conservative vector field, which comes as the gradient of your scalar potential, must be solenoidal or incompressible. Okay? So you can directly, if you know your scalar potential, then you can directly work out whether the vector field you can derive from that scalar potential, you can directly calculate whether or not that is solenoidal or incompressible by calculating the Laplacian. Okay. So just in the last couple of minutes to talk about a couple of things. So let me talk about exact differentials, which are in fact things that we've already come across previously. I'm not sure whether you'll have covered this in another lecture course or not, but it's essentially what we've already been doing in the case of conservative fields. So if I have some function f of x and y, then the total differential of f, which is not the same as the total derivative of f, the total differential of f, that is, what small change do you get in the value of f if you make a small change in x or y, is given by partial f with respect to x times the amount that you actually change in your x coordinate times partial f with respect to y times the amount that you actually change in your y coordinate. So an exact differential is a differential for which this is true. Okay? So you can have forms of differentials, as we'll see in a moment, for which this is not true, for which you can have forms of, you can have differential expressions where you have df or d whatever equals something dx plus something dy, where these cannot be true. It cannot be true that you have a single scalar function which has been differentiated with respect to x and then y to get those expressions. Okay? But ones where you can are called exact differentials. And you'll see that this is very similar to the expressions that we had for a conservative field. So if we have some scalar field f, and we calculate the gradient of f, and that gives us some ai plus some b times j. This means that a is df dx and b is df dy. So therefore, if df equals a dx plus b dy is exact, then ai plus b times j is a conservative field. Okay? So, and it won't surprise you then to find out that the standard tests we do of this is we use the test associated with the fact that second derivatives commute. So if your ai here is your df dx and your b is your df dy, then we take the derivative of a with respect to y, and that should equal the derivative of b with respect to x if it was an exact differential, which means if your field is conservative. Okay. And in general, if you have multiple combinations, if you have multiple variables, then an exact differential is only true if all of your pairs of second derivatives equal each other. So let me very quickly run through a couple of examples then to wrap up the lecture. So, are the following exact differentials: x dy plus 3y dx. Okay, so I've played an extraordinarily cunning trick on you here, and I've put the dy term before the dx term. So, what I would do is that's the y term, so that must be some df by dy. So I want to take the derivative of this with respect to x. So d by dx is 1. And then this I do with respect to y. D by dy of 3y equals 3. These two do not equal each other. This is not an exact differential. That means, just to be absolutely clear what that means, there is no single scalar function for which this could be the derivative of that function with respect to y, and this could be the derivative of that function with respect to x. So let's consider a second case then to finish off. Let's consider the form y plus z dx plus x dy plus x dz. Now, as it says here on this previous slide, you need to check that all possible two-way combinations are are equal in order to be certain. So the first thing I want to do then, so this is my my fx term, this is my fy term, this is my fz term. So let me first consider the comparison of the x and y terms. So I'll take the x term and I'll differentiate it with respect to y. So that differentiated with respect to y equals 1. And I'll take that and differentiate it with respect to x, and that equals 1. So we've passed that test. I'll now compare x with z. So I differentiate my x term with respect to z, that's 1. And I differentiate my z term with respect to x. And that passes the test as well. And then finally, I compare the y and z terms, and if I compare the y and z terms, I differentiate my y term with respect to z, that's 0, and I differentiate my z term with respect to y, that's 0, and there we are. We pass all 3 tests, and therefore this is an exact differential. Incidentally, what you're doing here is you're checking 3 relations because you have 3 terms. If you had n terms in your expression, then the total number of equations you would have to check would be n times n minus 1 over 2. And this is a number which comes up many times in physics and in statistics. It basically tells you the number of different unique combinations you have of your parameters. And we've done that. Okay, so we have 3 minutes. So I just want to very quickly check that you understand an expression. This is not really a core part of the course, but it's something you should know. So I'm going to very, very quickly do this in 3 minutes. So, you know that in 2 dimensions, if you go through some angle theta, which is in radians, where your length is r, and your length of your arc here is L, okay? In the 3-dimensional case, then we say that we have some solid angle theta, and this is an area that is now mapped out, where the area is the area of the surface of a sphere mapped out around that solid angle theta, where again my distance here is r. So this is for theta in radians, and this is for omega, my solid angle, in something which is called steradians. So have you come across steradians or solid angles before? Yes? No? Mostly not, I think is the answer. Okay. So what you should do, just as a quick exercise to make sure that you understand some of the basic properties of this, you should consider the case where you have some solid angle. So here's the line that connects my origin to my center point. This angle here, theta, we call the half opening angle. And this is my length r here. Okay? Then I will see that the area of the cap of this 3-dimensional cone will be the integral between 0 and theta, the integral between phi, which is my azimuthal angle between 0 and 2 pi. So phi here is my angle going round here. Okay? So you can see, if you think about it, that this area here is going to be the integral round here, the full 2 pi, with my angle going between 0 and theta, where theta is just the half of the total opening angle, of the surface element in spherical polars, r squared sine theta prime. I'm using theta prime here because theta is some constant that I want to evaluate for, d theta, d phi. Okay. So go away and evaluate that and check that you understand how you get the following answer. You'll get that the area is 2 pi 1 minus cos theta r squared, which then means that your solid angle, which is this divided by r squared, is 2 pi 1 minus cos theta. So what I want you to just quickly do is make sure you can do that evaluation, and I want you to think about what is the approximation for this in the limit that theta is a small angle, and I want you to go away and just check that you understand what the solid angle is for the whole sky. Okay, I'm going to stop there and I'll see you tomorrow. Thanks.